Well, welcome everyone to the morning session. So it is an honor to introduce William Kretschmer. William was my student at UT Austin. He is now a postdoc here at Simons, and I'm delighted to say he will be returning to UT Austin as faculty. He has been an amazing, sort of pioneer of the new realm of microcrypt or nanocrypt, whatever it's called, and he's going to give us his personal perspective on, where things are going, quantum cryptography and quantum complexity.
Well, thanks, Scott. Actually, does anyone know? Do I need to repeat the questions from the audience again, or?
Probably should. I think.
Yeah. Okay, I'll try to. Yeah, I titled this rather vaguely "Quantum Cryptography and Quantum Complexity" because I couldn't really think of anything better. But really, this talk is going to have two parts. So in the first talk, Scott said, I'm going to kind of survey the area and just give my own personal perspective on how things have developed. This is based in part on a talk I've given before a couple of times, including at a workshop in Banff. So some of you might have seen part of this before. But in the second talk, I'll be talking about a recent work with myself and Avishai Tal and Lo and Chen on quantum computable one-way functions without one-way functions. So let's get into it. So fundamentally, this is a talk about understanding the computational difficulty that's required to break quantum cryptography. And a good place to start in kind of understanding what we should expect in this field is by reviewing what we know about the hardness required to break classical cryptography. So classically, we kind of have a pretty good understanding that the computational complexity surrounding cryptography is closely tied to the P versus NP problem. In particular, we know that basically all forms of complexity theoretic classical cryptography cannot exist if P is equal to NP. I believe the earliest work to realize this was actually Diffie and Hellman for encryption. So they realized that to quote them, the cryptanalytic difficulty of a system whose encryption and decryption operations can be done in P time cannot be greater than NP, which is kind of a slightly funny phrasing, but all this is saying is that encryption breaks if P is equal to NP. And people have realized that kind of the same thing holds, not just for encryption, but actually for essentially all classical cryptography that relies on computational hardness. With just like a couple of exceptions like I/O, but we'll ignore those for now. We also have a good understanding that P versus NP alone is not all there is to say about the connection between complexity theory and cryptography, because we know that the existence of a hard problem in NP is not necessarily sufficient to imply the existence of cryptography. This is maybe best captured in Pagliazzo's 5 worlds, kind of the 5 possible resolutions to the P versus NP problem that have important complexity theoretic implications. And in particular, we know that basically cryptography can only exist in one of these 2 worlds, in either minicrypt or cryptomania, because essentially all complexity theoretic classical cryptography requires the existence of a cryptographic primitive known as a one-way function, kind of the central primitive in classical cryptography. And yeah, broadly speaking, I would say kind of the goal of some of the current quantum complexity theoretic research is to have a similar understanding to the classical world. So we'd like to be able to say, like, what is the quantum analog of cryptography cannot exist if P is equal to NP, and what is kind of the quantum version of one-way functions that captures the minimal amount of cryptographic complexity that is necessary in order to have any useful complexity theoretic cryptography. And what's been quite exciting and also surprising in recent years is that there's actually been evidence to suggest that actually all the way up here, all the way in Algorithmica, where P is equal to NP, quantum cryptography might still be possible, which is pretty surprising. Although I should note that when I say quantum cryptography is possible, I don't just mean QKD. So as I'm sure just about everyone here knows, there's this thing called BB84 quantum key distribution that is actually information theoretically secure. So using quantum communication, 2 parties can exchange a secret key over a public channel in a way that is physically impossible even for unbounded adversaries to break. But we also know that in many ways, in cryptography, BB84 is kind of an exception because, in fact, most other forms of quantum cryptography are provably broken by computationally unbounded adversaries. And so for basically all other quantum cryptography, you need to place some computational limit on the power of your adversary. And yet, nevertheless, what's kind of interesting is that some of the recent works has shown that you can, in fact, still have complexity theoretic cryptography, but somehow the hardness required to break it is not captured within the P versus NP problem. So in the quantum setting, there's new types of computational difficulty that underlie the existence of certain types of cryptography. And what have these works looked like? So largely, up until now, all the works that study these types of things have focused around a quantum cryptographic primitive that's known as a pseudo-random state generator, or PRSG for short. And formally, you can think of a pseudo-random state generator as being a quantum generalization of a pseudo-random generator. What that means operationally is that it's a quantum algorithm, an efficient quantum algorithm that takes as input a classical seed, but now the output is, rather than a classical string, it's some quantum state with the property that informally somehow the output should look like a random quantum state to all computationally bounded adversaries. And the exact way in which you define this primitive is not really going to be important for this in this talk, but what is going to be important for us is kind of the result that's been shown about pseudo-random state generators in a sequence of works that have basically shown that relative to certain oracles, so in a black box setting, pseudo-random state generators can actually exist even if P is equal to NP. So in other words, this is basically saying that even if you had the ability to solve NP-complete problems for free, at least in the black box setting, that would not give you the power to break pseudo-random state generators. There's been some slight variations on this, some involving P versus NP, some involving BQP versus QMA. But morally speaking, it's somehow showing that for this quantum cryptographic primitive, this pseudo-random state generator, its hardness is somewhere beyond NP. And as Scott noted, this has kind of inspired the coinage of this new world that's kind of completely orthogonal to Apocalypse's 5 worlds, this world of microcrypt, of cryptography that can exist even if... I thought it was Tomoyuki Morime, but does anyone want to correct me on that? Okay. Yeah. So, and one of the things people like to do is show these pictures of like all the new microcrypt primitives that people are studying. This is a diagram put together by Ora Satoth of all the, I guess, new quantum cryptographic primitives below 1A functions that people have started understanding the relations between, so that the black arrows are implications, the red arrows are separations. And yeah, there's just been a lot of work on trying to characterize the computational hardness and the minimal primitives within this space in light of the fact that somehow in the quantum setting we know that P versus NP is not going to be enough. And yeah, I think one of the main questions that really remains or open or that doesn't necessarily have a very clear answer at this point is what really is like the quantum version of this Diffie-Hellman principle that encryption breaks if P is equal to NP? Like, is there somehow a quantum generalization of this that like there's some complexity class that obviously captures the computational hardness required to break all quantum cryptography? And I think now, in light of some of the recent work on this subject, we can kind of say, or at least I like to say, that actually you can kind of break up the space of quantum cryptographic primitives into at least 4 different categories. So whereas classically, everything is kind of captured within P versus NP, in the quantum setting, it seems there's actually 4 different types, or I would say at least 4 different types of computational hardness that can show up for breaking quantum cryptography. This question?
Yeah, it's actually related to this. It's a high-level question related to this name, micro and mini, and so on. Like, when you showed these 5 worlds, like, what is the ordering of the worlds? Like, why is micro smaller than mini? Like, what do we supposed to take away from this intuitively?
Yeah. So the question is like, why is microcrypt below minicrypt?
And what does below mean also?
Yeah, so I guess it's below in the sense that it's even weaker forms of cryptography. So we know that like one-way functions imply a lot of the things in this microcrypt picture. So actually one-way functions are all the way at the top, and there's arrows kind of pointing down to everything below it. But like the reverse implication is not true. So somehow it's like even it's a weaker computational hardness assumption than the existence of one-way functions. That is the sense in which it is below minicrypt.
And is that the same with the 5 worlds? Like they're also in order somehow? Like,
Yeah, I guess maybe they're kind of in the opposite order though. Like I think it's also kind of an orthogonal access that microcrypt, I think, to like, you can't really just stick microcrypt on as to these 5 worlds. I view it as like a separate dimension in a way.
But if you are in minicrypt, you get everything in microcrypt.
Yeah, that's true. If you're in minicrypt, you get everything in
But
microcrypt.
not the other way. That's why.
Yeah.
Yeah.
Yeah, I mean, it's sort of like how if you're in Cryptomania, you get all the cryptography in minicrypt. And if you're in minicrypt, you get all the cryptography in microcrypt.
I mean, what it's saying is that even in Algorithmica, you can still have complexity theoretic cryptography.
Yes. Yeah.
So in some sense, it's a structure inside Algorithmica.
Any other questions? Okay, so yeah, what I'd like to do now is say a little bit about, kind of the 4 different classes, or what I like to say is the 4 different types of computational complexity theoretic hardness that show up in the existence of quantum cryptography that I guess the way I like to categorize these is somehow based on the syntax of the underlying cryptographic primitives. And I should note that this is really, this slide here is going to be kind of my personal perspective on the subject. I do not claim this is like a complete picture or that everything necessarily fits into only one of these 4 different buckets. Like there might be other buckets too, but somehow this seems to be like the most complete picture that we have so far. And so what are these 4 different buckets, these 4 different types of quantum complexity theoretic hardness that underlie cryptography? So the first, I guess, type of cryptographic primitives are those that break if NP is easy. So this is just all the classical stuff that we know and love. Anything where, say, the input is classical, the output is classical, it's computed by a classical algorithm. Examples of these are things like one-way functions and pseudo-random generators. These are things that we understand pretty well. The next bucket of cryptographic objects are those that break when QCMA is easy. QCMA being quantum classical Merlin-Arthur. It's one of the quantum generalizations of NP, in particular the one that consists of problems that you can verify efficiently on a quantum computer given a classical witness. And operationally, the types of objects that fit into this class are things where like you have some function that is still mapping classical inputs to classical outputs, but now this function is being computed by a quantum computer rather than a classical computer. And an example of something in this class might be what you could call like a quantum computable one-way function. So something that behaves like a one-way function, but the algorithm evaluating it is quantum. And just to give like a formal definition of this, we say that a function is a quantum computable one-way function if, first of all, there should be an efficient quantum algorithm that evaluates the function with high probability. But then you have the security guarantee that for all polynomial time adversaries, the probability that the adversary inverts the function successfully on a random input is negligible. And this is exactly the same as the definition of a quantum secure one-way function. The only difference is that the algorithm computing the one-way function is now perhaps a pseudo-deterministic quantum algorithm rather than a classical algorithm. And sort of the reason why you need QCMA instead of NP to invert something like this is that now in order to check that you have successfully inverted the one-way function, or the quantum computable one-way function, you have to pass it through a quantum computer. And that's now a QCMA problem rather than an NP problem. The next grouping of quantum cryptographic primitives are, I guess, those that break if sharp P is easy. And what tends to fall into this class are, again, things where the input is classical, the output is classical, it's computed by a quantum algorithm, but the difference is that now the algorithm is probabilistic instead of pseudo-deterministic. Or another way of saying that is that the challenge is sort of being computed rather than by a function, but by some relation. And kind of a canonical example of something that fits into this class is something known as a one-way puzzle, which is something I will define here. A one-way puzzle, or actually technically a distributional one-way puzzle, is defined in the following way. It's an efficient quantum algorithm that samples over a joint distribution of some x comma y, such that if you're just given one half of this joint distribution, so if you're just given y, it should be hard to sample from the conditional distribution of x given y up to some inverse polynomial statistical difference. So in other words, there's an efficient quantum algorithm that does this joint sampling, but if you want to do like conditional or post-selected sampling, then this should be computationally difficult. And kind of the reason why this type of primitive is broken if sharp p is easy is closely related to Aronson's theorem that post BQP equals PP. Somehow to break this, the natural way to break it is by way of using post-selection, and we know that quantum post-selection, its hardness is closely tied to the complexity class sharp p. I should note that it should not be at all obvious why this definition is useful, like what sort of cryptography you actually get from this, but this actually turns out to be a surprisingly useful and powerful definition. It actually implies things like quantum commitment schemes, so this is actually, yeah, like quite an interesting class of computational primitives. And another thing I should note is that actually another object that falls into this class of cryptography that breaks if sharp p is easy is pseudorandom state generators. Something I mentioned at the start of this talk that are basically like pseudorandom generators, but the output is a quantum state instead of a classical string. This containment is not obvious. This containment that pseudorandom state generators break if sharp p is easy, because operationally it seems like a pseudorandom state generator is something that produces a quantum output rather than a classical output. But it turns out that like when you have sort of a notion of multi-copy security, so the challenge is secure against adversaries that can access an arbitrary number of copies of the quantum state, then there's some way you can sort of perform measurements on the quantum state and get some classical output that can always be turned into something that operationally looks like this, where you have the challenger is basically producing a probabilistic classical output that the adversary is trying to invert. So that's the third class of cryptography that breaks if something is easy. Kind of the last class of quantum cryptographic primitives are those where we actually have no known upper bound on the computational difficulty of breaking them. And the things that tend to fall into this class are those where the input, rather than being anything classical, is now a quantum state. So the challenge that the adversary gets is something quantum, and kind of canonical examples of things that fall into this class are things like quantum commitment schemes, or equivalently so-called EFI pairs. I'm not going to define these unless someone wants me to, but I guess the intuition here for why we don't actually know of a complexity theoretic upper bound on breaking these things is that, so assuming these are actually not information theoretically secure, so there is some information theoretic attack on breaking these things, that means that there's like some measurement that you can perform on the quantum state that will somehow distinguish or break the security of the primitive. The challenge is that we don't know in general whether access to a sufficiently powerful classical oracle will give you the power to actually measure in that basis. This is closely related to, and actually kind of tantamount to, something known as the unitary synthesis problem, which is one of the big open questions in quantum complexity theory. And the unresolved status of unitary synthesis is kind of why we don't know how to place an upper bound on the complexity of breaking these things in terms of standard complexity classes like NP or QCMA or whatever, where the inputs are classical objects rather than quantum objects. So this is kind of like my personal take on how you should think of different types of computational hardness and their relation to cryptography. And what's sort of nice about this picture too is that you can very easily place some of the recent developments, some of the recent oracle separations into this picture. And what do I mean by this? So for example, I had this result in 2021 showing that there's an oracle, a quantum oracle, relative to which pseudorandom state generators exist, but BQP is equal to QMA, and so QCMA is easy. So in other words, one way to interpret this result is as showing that there's a separation between this class of stuff that breaks if sharp p is easy and this class of stuff that breaks if QCMA is easy. In 2024, so more recently, Lombardi, Ma, and Wright had a result showing kind of a separation between these two classes by showing that you can have commitments that exist even if sharp p is easy, although this is with a caveat that technically the separation only holds for a restricted kind of adversaries that only make parallel queries to the oracle. And one of the big questions that this kind of leaves open is whether you can separate these other two classes, so whether you can find a an oracle relative to it, you have cryptography that breaks if QCMA is easy, or I guess another way of saying it, you have that NP is easy, but nevertheless you have something like a quantum computable 1A function. And this kind of now brings me into the second half of this talk, where we do exactly this. So as you can probably guess from the title of this work, we build quantum computable 1A functions without 1A functions. This is based on joint work with Lo and Chen and Avishai Tal. Actually, any questions here before I move on? Yes?
When you say QCMA is easy or SHA-P is easy, you mean the equality SHA-P is BQP or?
Yeah, okay. What do I mean by like QCMA is easy? I was being a little bit deliberately informal about this. I guess you should just think about it as like this thing is equal to BQP. You can maybe also just think about it as what happens if I give out an oracle for QCMA or an oracle for SHA-P. But yeah, I was also kind of being deliberately vague because some of these are slightly qualitatively different in this regard. So in this oracle separation by myself from 2021, this is an oracle where BQP is equal to QMA. But in some of these other oracle separations, you get like P is equal to NP or something. So whether the collapse is to P or to BQP is like a difference I kind of just wanted to sweep under the rug.
So our result that there's an oracle where P equals NP, but BQP is different from QMA would be sort of like a necessary condition for this new result, although not a sufficient one?
Yes, very good observation, yes. An oracle where P equals NP, but BQP is different from QMA or QCMA. And this is no coincidence that, as we'll see, that this result will use very similar techniques.
Yeah.
Other questions? Okay, good. So, let's move on to stating what is the main result of this work. So, our main result is that we construct an oracle, actually a standard classical oracle, such that P is equal to NP. So, all complexity theoretic classical cryptography can be broken efficiently, and yet nevertheless you have quantum computable 1A functions relative to this oracle, or in fact even quantum computable trapdoor 1A functions. So a stronger primitive that actually allows you to construct more powerful forms of quantum cryptography, like public key encryption, or what was the other one? Oblivious transfer, for example. And kind of another way of summarizing this work is that what we do is we build a classical communication, quantum cryptomania, in classical algorithmica. Like somehow quantum computers, you get really powerful cryptography in the form of public key encryption and whatever you want, but classical computers, P is just simply equal to NP. So a very strong separation between classical cryptography and quantum cryptography. What I want to do now is say a little bit, before I move on to talking about the technical details of how we prove the separation, I'd like to just go back to this picture and discuss some of maybe the biggest open problems that still remain, kind of the bigger consequences of this work. And I would say, maybe one of the biggest questions that still remains in light of the separation is whether you can actually come up with any real-world candidates of, say, a quantum computable 1A function that would resist even like P is equal to NP, or at least plausibly so. This seems like a pretty challenging problem that's actually closely related to whether you can find, say, a non-black box instantiation of the correlation problem that would say give like a candidate separation between BQP and pH without an oracle, so just in a white box setting. A second natural open question for future work is whether you can strengthen our separations to not just quantum computable 1A functions, but other quantum computable primitives like quantum computable I/O or quantum computable one-way permutations. I should note that, and actually this will become apparent when I talk about the oracle construction, our proof does give seemingly a pretty general way to build oracles that plausibly give you such separations. The hard part is actually showing that the security of the quantum primitive actually holds relative to these oracles. So in other words, you can very easily construct an oracle where P is equal to NP, and you plausibly have some instantiation of this primitive, but there's just a little bit of work, or maybe not so little amount of work, in showing that the primitive is actually secure. And then finally, maybe the last natural open question is whether you can actually get like a fully classical separation for sort of these two errors here. So I think I mentioned how both of these separations have some caveats. This first separation is not a standard classical oracle separation. It is a quantum oracle separation. So the black box that is being used for the separation is a unitary oracle. For the second result by Lombardi, Marr, and Wright, the oracle separation only holds against a restricted class of adversaries that make parallel queries. And whether you can get fully classical oracle separations for these two would also be nice to know, because then that would really give us the strongest evidence that we could hope for that all four of these classes are really distinct. But of course, at least in our work in the separation between the NP and QCMA difficult classes, we really do achieve a fully standard classical oracle separation. So that about summarizes all I wanted to say about the open problems and kind of the implications of this work. My plan for the rest of this talk is just to say a little bit about what goes into actually proving the separation and kind of the key ingredients in the oracle construction, because I think to a lot of people the proof here is still a little bit mystic and looks kind of magical, and I want to at least convince you that maybe the ideas underlying it are not actually that complicated. In particular, in many ways, the oracle construction is pretty intuitive. So that's what I'm going to try to explain next. But maybe before I move on to that, let's just check if there's any more questions. OK, good. So yeah, let me explain how we build this oracle, which, again, just to remind you, we need to accomplish two things. First off, this oracle should collapse P to NP. And second, we should have a quantum computable one-way function relative to this oracle. So we're going to build this oracle in 3 stages.
Sorry, the one-way function has classical output or quantum output?
Classical. The one-way function has classical output.
Yeah. OK.
Yeah. Yes?
Question about the previous slide. So we know that Kepler one-way functions, I guess, imply oblivious transfer and so on. Is it totally obvious that this is friendly to quantum attackers, so the reduction is nice? Something this reduction don't work.
Yeah, as long as the reductions, I forget exactly what the terminology is, but this something fully black box or something, then they go through. Yeah. So yeah. I mean, it is like slightly non-trivial. I think we have a couple of pages kind of dedicated to showing that yes, indeed, these quantum computable trapdoor one-way functions give you the primitives that you expect, but yes, all of these reductions go through. Yeah. Good. So let me explain how this oracle is built. As I mentioned, it will be in 3 stages. In the first stage, OK, I should also note, actually for this oracle construction, I'm not going to do the trapdoor part. I'm just going to show you how we get one-way functions. The trapdoor part is conceptually similar, but it'll just be a little bit more structured. If you just want to get one-way functions relative to an oracle where P is equal to NP, or quantum computable one-way functions, here's how you do it. You start with a uniformly random oracle F. So you have just written out the truth table, say restricted to n-bit inputs. Just for each input, I choose uniformly random. The output of F is either 0 or 1. This is a pretty standard object in classical cryptography. And then what I'm going to do is turn F into what I call a correlation encoding. What this means is that I'm going to construct a function F bar that takes in 2 inputs. So it takes in X and then maybe a second input Y, where the truth table of this function is going to be sampled from one of 2 distributions depending on the output of F. So if F of X is equal to 0, I'm going to sample the truth table of F bar of X on its second input to be a uniformly random Boolean function. On the other hand, if f of x is equal to 1, I'm going to sample this distribution of this f bar to be a so-called correlated distribution, which is something I'll define in just a little bit and say what the significance is of correlation. But for now, you can just take my word on it that if it's zero, you take it from the uniform distribution. If it's 1, you take it from some other distribution. And then finally, the oracle. The oracle O that is in our construction is basically an oracle for the polynomial hierarchy pH raised to f bar. So it's an oracle that lets you solve any problem in pH raised to f bar. This is kind of lying just because what it actually means to give out an oracle for pH is kind of subtle, just because the polynomial hierarchy is not believed to have complete problems unless it collapses. And so it's not exactly like an oracle for pH, but like morally speaking, this is what it is. And indeed, like, one of the immediate consequences of this oracle construction is that it's like quite obvious that P to this oracle is equal to NP to this oracle, just because P to the pH equals NP to the pH. Now, kind of the one thing I didn't tell you is like, what is this correlation thing and what is the significance of it? So I guess actually I'm not going to define exactly what correlation is. If you were here for Andrew's talk yesterday morning, you might have seen it, but really the only thing you need to know about correlation is the significance of it, which is that it was used in this result by Raz and Tal in 2019, which showed that to the polynomial hierarchy, correlation is actually indistinguishable from random. So to pH, to this pH oracle, somehow it shouldn't really be able to tell the difference between when you're sampling a uniform truth table from a correlated truth table. But on the other hand, quantum algorithms, in other words BQP, actually can efficiently distinguish whether a function is uniform or correlated. So again, I claim it's like pretty easy to show that P is equal to NP relative to this oracle. What is the candidate quantum computable one-way function construction relative to this oracle? So I guess the key point is that because BQP can efficiently distinguish uniform truth tables from correlated truth tables, then a quantum algorithm given access to this function f bar can actually use it to compute the underlying random oracle f. So by querying f bar, say on some input x, you can use it to extract f of x. And once you are able to compute f on a quantum computer, then there's just like a completely standard way to go from a random oracle to a one-way function. And that one-way function, which is now quantum computable because you need a quantum algorithm to evaluate this correlation, that is the candidate quantum computable one-way function. And kind of the main remaining work is just to show that construction is indeed secure in the presence of this oracle O. Any questions about this? Yes?
Suppose you wanted to use this result to say something about like the non-oracle setting, or like down the line at some point. You would want to, I guess, like instantiate something that looks random for your app. And then I guess the question is like, should this be taken as evidence that things will hold up outside of the oracle?
Yeah. So the question is about how do you instantiate this in a non-oracular setting, and that's very much unclear. And again, kind of the difficulty is closely related to the fact that we really don't know how to instantiate something like correlation in a white box setting. So it's really not at all clear whether this gives any evidence for the existence of a white box primitive that behaves like this. But yeah, it's a good question.
So, does the fact that you have to take pH to the f bar impose further difficulties? Does that or the function become that much more complex?
So what do you mean by does the oracle become that much more complex?
If you were to try to, in the spirit of this question.
If you were to try to instantiate, yeah. Well, okay. I mean, I guess you should, in a way, you shouldn't expect necessarily to instantiate this oracle unless you believe that P is equal to NP, right?
Yeah.
Yeah. I mean,
right.
Yeah. In a certain way, it is kind of funny to talk about a hypothetical world where P is equal to NP if we don't really believe that P is equal to NP, but it is something that we can do, and it's the only meaningful way to say that, yes, the hardness of this primitive is somehow more than P versus NP.
Right. I mean, you could hope to instantiate part 2 of the oracle.
Right, yeah. You could hope to instantiate F bar.
Mm-hmm.
You probably could not hope to instantiate O itself. Good. So this is the oracle construction. To tell you kind of the key ingredient that goes into the proof of actually establishing its security, I need to take a slight diversion and talk about something that maybe on its surface looks pretty unrelated, but that is, I guess, AC0 circuits and sensitivity. Oh, there's a question, yes.
Just maybe a simple one, like why do you need the pH instead of just raising it in P to the oracle? Like, why can't you just give it an oracle for NP and then?
Yeah, okay, so yeah, why can't it just be NP to the F bar instead of PH to the F bar? The reason is that we need P to the O to equal NP to the O. The problem is that P to the NP is not believed to equal NP to the NP. Yeah. So you need some sort of recursive construction that really does make P equal to NP. I suppose if you just wanted something weaker, instead of like an oracle separation, you just wanted like a fully black box separation, you might be able to get away with something like that. But for an oracle separation, it does seem you need essentially this construction. Yes?
What does pH to the F bar mean?
Yeah, I kind of swept that under the rug too. What does pH to the F bar mean? Because I am lying here. Like,
I mean, you can just say like it means that you can make queries to the kth level, of the hierarchy if you spend n to the k time.
Yeah, exactly. Yeah, you can spend. I mean, maybe it's not exactly like that. It's like maybe n to the 100k time. Like,
right.
Yeah, if you spend n to the 100k time, you can solve a problem in the kth level of the hierarchy. Yeah. There is like a fully. It's like recursive, but pretty simple way to define what this oracle is. But yeah, morally, it really is just an oracle for pH, even though that's not technically true. Anything else? Okay, good. So yeah, we're going to take a diversion and talk about sensitivity of Boolean functions. So say we have some n-bit Boolean function f. We have an n-bit input x. There's this function that's well studied in computational complexity theory, known as the sensitivity. It's closely related to the I guess, fairly recent resolution of the sensitivity conjecture. This is the same sensitivity that showed up in that conjecture. And what is the sensitivity of a function f on an input x? It is defined as the size of this set, so it's the number of indices I between 1 and n, such that if you flip the ith bit of x, and you compare f of x and f of what I'm denoting as x, x or I, this is the number of indices I for which flipping that bit changes the value of f. So those are kind of, this is the set of sensitive bits of f on input x, and the sensitivity of f just counts the size of this set. And there's this theorem about AC0 circuits, which again, I'll explain how AC0 circuits are connected to this, but AC0 circuits, again, meaning constant depth circuits of unbounded fan-in and or and NOT gates. There's this theorem that says that with high probability over a uniformly random input, the sensitivity of an AC0 circuit is quite small. It's actually like polylogarithmic in the input length, assuming the AC0 circuit has like at most, say, polynomial or quasi-polynomial size. I don't have a reference written down for this theorem because I'm actually not sure like what is the right reference to give. So in a way, I believe that the first paper that actually like made this theorem explicit in the form that's kind of stated here was this paper by myself, Aronson and Ingram in 2022. But actually, if you look at that paper, we really attribute the proof of this to a personal communication with Avishai Tal. And indeed, actually, the proof that something like this result is kind of implicit in this prior work by Gopalan, Servedio, Tal, and Victorson from 2016. And moreover, I think in many ways, this is really kind of a fairly simple corollary of Linial, Mansour, and Nissan from 1993, who stated a closely related but weaker statement that the average sensitivity of an AC0 circuit on a uniformly random input is quite low. This is basically a concentration statement, a concentration inequality generalization of that average sensitivity statement.
You can't just use Markov's inequality? Because with high probability, you mean very, very.
Yeah, what that with very high probability is essential, and So this is okay. So this is like a nice theorem about AC0 circuits. What it turns out that we need to analyze this oracle construction is a generalization of this statement that requires kind of thinking about sensitivity in a slightly different way. So I'm actually going to redefine sensitivity in an equivalent, but I guess conceptually different way. So right now, the way we define sensitivity is as the size of this set, so just the number of sensitive bits of this function f on this input x. But here's a different way to think about sensitivity. So imagine I am going to consider a distribution over some set of strings y that will depend on x. And the way I'm going to sample y is going to be the same as x, except I'm going to pick a uniformly random input, index between 1 and n. And for that index I, I'm just going to sample the value of yi to be independently uniformly random between 0 and 1. So y will be the same as x, but just like in a single random place, I will just toss a coin and randomly sample that bit. So one thing you can do when you consider this sampling distribution is redefine sensitivity in the following way. You can define it as 2 times n times the probability that f of x is different from f of y when you sample y from this distribution. And so why is this true? Well, what is the significance of this 2n? So the 2, the factor of 2 is just because there's like a 50% chance that when you sample this yi, it will actually just be the same as xi, and a 50% chance that it will differ. And then this factor of n is just because there's n possible choices, and to get back from this, which is counting the number of indices, to convert that to a probability, you have to multiply or divide by this factor of n. So what do we get out of redefining sensitivity this way? So it turned out there's kind of a natural way to generalize this to inputs that are not just n bits long, but that are actually basically, I guess we'll say n by n matrices. So instead of having, an input x that's just n bits, it's going to be n bits long and n bits wide. And now we're going to have a function f that takes in n squared bits. And now, what we're going to do when we sample this input y, so instead of sampling yi to be random in 0 or 1, we'll sample it to be from, say, some distribution d, actually an arbitrary distribution d, over n-bit strings. And what you can do, you can sort of define a generalization of sensitivity to these kinds of functions and these kinds of inputs. We'll define what we'll call, I guess, the d sensitivity of f on x, I'll denote by s sub x to the d, as basically the same quantity, so it's 2 times n times the probability that f of x differs from f of y when you sample y in this way, which, just to remind you, is you take x, you pick a uniformly random row of x, and then you sample that row from some distribution d. And okay, what is the key theorem that we prove? The key theorem that we prove is that this distributional sensitivity for these matrix-valued inputs also satisfies a concentration inequality for AC0 circuits. So in particular, if you sample a random input x from d to the n, meaning you just independently sample each row of x from whatever distribution d, then with very high probability, the d sensitivity of f on such a randomly chosen x is quite small. It's like polylog n, which is very small compared to n. Yes?
I suppose you used n for the number of rows and the size of the rows, so you can do the correlation thing. But is this also true if your rows are different lengths?
Okay, yes. Here, I've written it so that the rows and columns are both n, but actually it's really n by m. But you can just think of it as being n by n. Yeah. Yes.
Sorry, I just realized I'm lost because so the previous slide you had you're going to raise the correlated random oracle to the pH or vice versa, and that's it. And then what is the motivation for this?
Yeah, it'll be. I'll explain on the next slide. It should not be obvious why any of this is related to the oracle construction. If you're very lost, that's good.
I'm not lost. Is that bad?
Good. So let's take this and view it back in the context of our oracle construction, which, just to remind you, we start with this random oracle f, we turn it into this correlation encoding, and then we hand out an oracle for pH raised to this correlation encoding. So what are the key things to note here? So the first thing that maybe partially answers this question of what is pH have to do with AC0 circuits? So actually, this connection between pH and AC0 is pretty old. It dates back to first Sachs and Sipser in 1984, who basically observed that if you have a pH algorithm that makes queries to some oracle, then you can always equivalently view the behavior of that algorithm as being defined by some corresponding exponentially large AC0 circuit whose input is the truth table of that oracle. So this correspondence between pH and AC0 goes back over, I guess, 40 years at this point. And it's actually interesting to note also that one of the original motivations for studying AC0 circuits was in order to prove oracle separation results about the polynomial hierarchy. People were not just studying it because they cared about circuit complexity, they were also studying it because they cared about proving oracle separations involving pH. And this is just another example of that, just 40 years later. And so what is the significance of this distributional sensitivity? So somehow, it turns out that if you look at the distributional sensitivity of, I guess, this oracle O, so this pH algorithm or AC0 circuit that is querying this F bar, then this distributional sensitivity under essentially the distribution where you're sampling these inputs, so you're sampling truth tables from in this form where you take first a random function and then you take its correlation encoding, this distributional sensitivity measures exactly the probability that O changes when f of x changes in a random place. So in particular, if you look at, if you consider what happens when, say, you flip a single bit of f of x from 0 to 1, and thus change the corresponding row of f bar of x from correlated to uniform or vice versa, then kind of the probability that changes the output of this oracle O is exactly this distributional sensitivity. And by having a bound on this distributional sensitivity, you can use this to basically show that you can sort of resample parts of the oracle in a way that even a quantum algorithm that queries this oracle O cannot distinguish. So like if you just change f of x in a few places, which would say change the value of the 1A function on certain inputs, then if you do this carefully, a quantum algorithm will not be able to detect this change and thus will not be able to notice that you've actually changed the value of the 1A function, and hence you can use it to argue that the quantum algorithm is not successfully inverting the 1A function. So this is kind of the key idea that goes into this. So are there any questions about this? Because I'm happy to take as much time here as I want, because this is pretty much where I was going to wrap up. Yes.
Can you say in I guess one sentence how? So these are secure against quantum adversaries, first of all.
Yes.
So can you just say in one sentence, a high level, how? I guess because in general, when correlation shows up, you expect a quantum algorithm to be able to succeed at what it's trying to do.
Right. Yeah.
Secure.
Yeah. I mean, okay. So sort of the intuition is that yes, having a quantum algorithm lets you go from f bar to computing f, but somehow having this pH oracle does not make it any easier to invert the 1A function, because I guess the intuition is that since correlation looks random to pH, having access to pH to the f bar from the perspective of the quantum algorithm should not be more powerful than just having access to f bar alone. And if you have access to f bar alone, it's actually pretty straightforward to show that this is like a 1A function, just because it's essentially no different than a random oracle. So kind of what this proof is doing is showing you that having this additional power to not just query f bar directly, but to query pH to the f bar is not helping you, because this pH to the f bar somehow cannot be sufficiently sensitive to detect small changes that are being made to the oracle. Any other questions?
maybe another intuition is that if you just change like one entry of this f function, then a quantum algorithm would not notice it, right? That's like BBBV. That's
right.
So it's true that you can go from f bar to f, but since you only change one entry in like exponentially long thing, that's not.
So you've got the combined power of BBBV and Ras-Tal, preventing you from breaking this one-way function.
Yeah. There is a BBBV underlying this, and also Ras-Tal.
Right.
Yeah.
Blocking off the two different, one by using Oracle 2 and the other by using Oracle 3.
Yes.
So you said that this framework seems like it might extend to do the other things that you want to do for other primitives. Can you say a little bit about that?
Yeah, I can say a little bit about that, and maybe I can say like what is the difference? So this is how you get one-way functions, quantum computer one-way functions. How do you get trapdoor one-way functions? The difference is instead of starting with this random oracle f, you start with an oracle f that computes a trapdoor one-way function. And yeah, the candidate construction then is just replace f with whatever you want that computes your favorite primitive. So, plausibly, if you replace f with something that computes I/O, or if you replace f with something that computes a one-way permutation, then you would expect that kind of intuitively this oracle construction should still, give a quantum computal instantiation of that, even if p is equal to np, because again, it is completely clear that p is equal to np relative to this oracle construction, regardless of what f is chosen to be. The only thing that's not clear is whether that quantum instantiation of this primitive is actually secure. And what this lemma lets us do is kind of analyze primitives where somehow the security is based on a game where you're just changing the oracle in a single place. But it's harder when you have to deal with more structured oracles. Things like permutations are more tricky because you can't just change the oracle in one place. You have to like change the oracle in multiple places if you're resampling it, or similarly for I/O. And that's kind of why we can get one-way functions. Less obviously, you can get trapdoor one-way functions, but by some resampling strategy that only changes the oracle in a small place. But
Wait a minute. How do you get a trapdoor one-way function? Because you can't get that from a random oracle.
Yeah. Okay. So how do you get a trapdoor one-way function? There's like three parts. There's like an oracle that gives you there's like an oracle that maps a secret key to a public key. There's an oracle that basically does the encryption given the public key and an input. Both of those are just random oracles. And then finally, the third oracle is just, it does the inversion of given the secret key and the corresponding output of the second oracle to produce the input.
Fine, but then underlying all of that, there's just more BBBV and there's more generalization of Ras-Tal.
Yeah, underlying that is exactly the same proof strategy fundamentally, that somehow you reduce it to showing that you can, it's like a more complicated hybrid argument, but fundamentally it is BBBV layered with Ras-Tal.
Yeah. Yep.
And this is, I was just going to wrap up here, to remind you that this is how we prove the main result, that there's an oracle relative to which p is equal to np, and quantum computal trapdoor one-way functions exist. And yeah, I'm just going to stop here. I'd be happy to finish with any more questions.
Great. Any other questions for William? So do we have all the oracle separations we want on like the right hand side, like the sort of the unitary synthesis side? Or?
No.
No, we don't.
Yeah. Where was it?
Yes. Yes. Yeah.
Whoa. Yeah, I would say so. Again, this LMW result, this is still only against parallel query adversaries.
Oh, right.
Yeah. Whether you can get like a fully standard classical oracle separation, and also the Kretschmer 2021, that's also a quantum oracle. If we can do a classical oracle, that would be nicer.
I see.
Are there any obstacles to making that a classical oracle? Like, would that separate QMA from PCMA or something? Or
Wait, sorry. Are there any obstacles to making what a classical oracle?
the K21?
The K21? The obstacle is that we don't know how to build a classical oracle where P is equal to QMA but is different from PP. We got very close to this in this paper with myself, Aronson, and Ingram in 2022. We can sort of show that relative to a random oracle, PP is not contained in QMA to the QMA to the QMA, et cetera. But yeah, turning it into something where P is equal to QMA but is different from PP seems to be difficult.
Now, in terms of like real instantiations of these different kinds of crypto. Okay, I mean, of course, on the left-hand side we have that, and then for the sharp P, there's the recent thing by like Dakshita, Karana, and Tomer, right? Although that depends on the permanent of Gaussian's conjecture. Right, and then I guess maybe like on the right-hand side, we would have candidate instantiations too. That would just look like random quantum circuits or whatever, and then it looks like the one where we don't have any candidate instantiation is the second one.
Right, and it's also kind of funny. Yeah. So we don't. We have candidate instantiations here and here, but maybe not in the QCMA bucket.
Right.
And it's also interesting how conversely, like we have the. In terms of oracle separations, the opposite is true. We have the best oracle separations for that bucket and the worst ones for the other buckets. Yeah.
All right. Any other questions?
Yeah.
So how does this picture change if this unitary synthesis conjecture is true or false? I don't know how it was phrased, but like if you can,
Okay. If I have like a sort of an unpublished result about this, but you can sort of show that if unitary synthesis is easy, then you can place at least an NX upper bound on breaking these things. Yeah.
do you have what people believe about the conjecture, or
what people believe about unitary synthesis?
Unitary synthesis, yeah.
I think most people believe that unitary synthesis is not easy, in which case that result wouldn't tell you anything. But yeah, I don't know. I've gone back and forth personally on whether I believe it or not. So.
All right. Any last questions?
Yeah. So if you could construct peaked circuits, could that be like an instantiation for the second box?
If you can construct peaked circuits, would that be an instantiation? Maybe. I mean, it would at least, okay, if you could construct peaked circuits, maybe it would at least be quantum computable, not classically computable. But less obvious are, is it a one-way function? And is it a one-way function that also is harder than NP? Yeah, those are both non-obvious. But maybe, yeah.
All right. Anyone else? All right. If not, let's thank William again.
Thanks.
There's now a half-hour break, and then on the schedule, Mark Jandry is up. Is Mark here, by the way?